Alright, so good morning. I'm Calvin, and today I'm going to talk about the laminar structure in fish gills. And here's the background. Unlike other vertebrates on land, fish respires through the gills, and the gills capture oxygen content via a well-ordered laminar structure. And gills are evolved to optimize their oxygen diffusion rate. And here are some of the observations. The gill interlaminar distance varies a little, while various species of fish have different fish size, and they can vary by a million times, but their laminar structure, the size of it only varies by less than 6 times. And here I'm going to talk about the diffusion of oxygen into the gill filaments, and here's a video. I guess I'll just. So for some of the fish, they usually gulp in the water into their mouth, and the internal wall of their mouth contracts and push the water out of their gills. And this is how the so-called laminar structure works, and this is inside the fish gills. And here we can see the blood of the fish going through this laminar structure. After the blood goes through the fish, the body of the fish, their oxygen level of the blood will be usually low, and the water that goes over their laminar structure have a higher oxygen content, and the oxygen would diffuse into the blood inside the structure. Here are some of the parameters we use to formulate some of the diffusion equations. You can just take a look afterwards if you wish to. Here are some of the other parameters, which include the Stewart number and the Reynolds number here. The Reynolds number is defined as the width of the laminar structure. They call it the interlaminar distance, and the length of the channel. And here are some of the typical values of some of the variables. As we can see, the Reynolds number is around 10 to the negative 3, and which indicates the laminar flow in the gill. Here are some of the assumptions that we use when we are deriving the equations, which is that the change of oxygen partial pressure is negligible across the laminar structure, inside the structure, due to the rapid adhesion between the capillaries and the oxygen molecules. That means after the oxygen diffuses into the blood, they spread out really rapidly, so we can just ignore the distribution. Also, the laminar height is much more than the interlaminar distance, which is the width, so that we can simplify these equations afterwards. And since the flow rate is laminar, the entrance effects can be ignored. And here are some of the equations that we use to derive the diffusion rate. Here we can see that the flow rate of oxygen over the distance of x is formulated by the convective mass transfer coefficient, the solubility of oxygen in the water, the wet parameter, and the partial pressure difference between the water and the blood. Here are just some of the simplifications here, and after solving for the equation, we get the partial pressure of the oxygen in the water. And another expression to describe the oxygen mass transfer is the mass transfer of the oxygen times the pretty much the partial pressure drop of oxygen in the water. And we can also use the Poiseuille flow solution to describe the streamwise momentum conservation, and then we can get an expression that describes the mass transfer of water. After combining all the equations above and differentiate it by the width of their structure, we can get the optimum interlaminar distance, which is this. As we can see here, their width, their parameter d is up to the order of 4, which means that it's pretty inner and irresponsive to change of other parameters, including their length of the structure and their pumping pressure. Here are some of the experiments and evidence that the paper used it to support their theoretical values. The first one is that they examined 75 species of fish, and they found that their laminar width is actually within 20 to 110 microns, which is a relatively small range considering that the fish body sizes varies by 1,000,000 times. Also, if we look at the trend of the or the ratio between the D and L, which is the ratio between the width and the length, they follow the same trend, and most of them fall within their expected values. And if we look at the picture below, we can see that although the distance or the dimensions of the gill or the structure does increase with their body size, but it's pretty small. If we look at here, we can see several groups of labels. It's because different fish have different ways of breathing. Some of them, just like what we saw in the video, they gulp in the water and force it through their gills, but some fish just swim real fast and they just ram into the water and force it out of their gills. Another experiment they did is to make an artificial laminar structure made of microfluidic chips, and they just pump water into, or let me just say, they just pump the oxygen-rich water over the structure, and they have some of the oxygen-depleted water inside the structure, and they measure the rate the oxygen diffuse into the internal structure. And they found out the data points as shown here, and they match their curve that describes their theoretical values. So we're human, so why does that matter to us? Because the diffusion mechanism is not unique to the fish gills. Other animals breathe just like the insects. They breathe through their membranes and exoskeleton. Humans also breathe through our lungs. And all of them depend on the diffusion of oxygen. And here just a video talk about that. And I'm just going to skip some of them. And And as we can see here, this is actually an air stat inside our lung, and they call it the alveoli. The membrane of it is only 1 cell thick. The oxygen can diffuse into our red blood cells through the membrane, and the carbon dioxide can diffuse out of our red blood cell through the membrane. And this is controlled by the partial difference in the pressure of oxygen and carbon dioxide. Okay. So the main takeaway of this presentation is that the oxygen flow rate is decided by the oxygen content in the water or air, and the increased size of laminar structure has little to help with the increasing oxygen exchange rate. The optimal interlaminar distance is dependent on the pumping pressure, although it's not really that responsive. Here are some of the applications that you can think of about this research. The first one is the medical one. If we can understand well about the diffusion rates of oxygen, we can design some artificial lungs for organ transplant. Another one is the science. It's more on the biology or archaeology side, which is that this is one of the reasons why ancient insects and dinosaurs have enormous body sizes due to the atmosphere they lived in. And the final one that I can think of is sports, because if we understand the maximum oxygen exchange rate, which is dependent on the diffusion, we can actually boost our sports performance. Actually, the artificial lung technology exists for diffusing oxygen into the blood. And there's only one challenge because it clogs a lot, and they still have to overcome that before it becomes useful. And the second one would be the science that I talked about. So the insects reached maximum sizes at around 300 million years ago, and the oxygen level in the air is much higher than what we have nowadays, which is more than 30% in the air compared to the 21% that we have nowadays. And finally, I don't know if some of you have tried, like when you try to start running, you find a struggle with your breathing work. It's just because your body is not adapted to such an intense workout, and your body actually urged you to breathe more, but after you breathe more than an overly rapid pace, it doesn't really help with the diffusion rates of the oxygen because it's controlled by the positive pressure in the air. If you're breathing too much, you're just trying to stretch out your diaphragm, but it's not helping much. But for some of the more experienced athletes, they train a lot and they train every day. In turn, they are really tolerant to the carbon dioxide buildup in their body, so that they are not that reactive than when they are feeling a short of breath. Also, trained athletes possess a greater blood volume in their body, so that it helps them with their oxygen diffusion rate, so that they don't have to breathe as much, but they still get more oxygen for their body. And that's why the training and conditioning for the athletes really mattered. And I think that's all I have for today. Are there any questions?
Questions for Colin?
Could you go back to the slide where it talked about the insects and how they were much bigger back then? Because I didn't understand the relationship between the fact that you had more oxygen in the air and bigger insects.
Yeah, so that actually has to do with their volume to their surface ratio. As you know, a larger object has a smaller surface area when compared to their volume. So that larger insects require more oxygen supply to their surface in order for them to survive. So as we have more oxygen in the air 300 million years ago, they can grow much bigger than what we have nowadays.
So, what animals are the ram feeders, and what animals are the blah, blah, blah?
Yeah. I think we have something here. They call it the ram ventilation type and the branchial pumping. I think the pumping is like the one that gulps.
So,
Yeah.
if a shark is chasing you, if it goes downstream, it's going to die. Because if it goes downstream, let's say it's going at the same velocity as the stream's going down, then it's not going to have any any velocity around its gills, right?
What you mean is like it's swimming backwards or?
Let's say the flow is going this way and it's swimming with the flow.
But I mean, the sharks and some fish like tuna, they swim really fast. I mean, I remember they swim over like 40 miles per hour, so I think they can catch up with the flow if they adapt like such ramming type of.
If you had like a water tunnel at 40 miles per hour and you put a shark in there, it could not get any oxygen because you have to have new oxygen at your gills, right?
But it's relative, right? So if it's swimming in a stream that is like 40 miles per hour, so it can swim up to 80, right? to word that way.
Don't tell me there are sharks in streams now, because I have enough trouble with the ocean.
But I mean, theoretically, they just
Yeah, I see.
yeah. But I mean, if let's just say for some of the fish, if they breathe by like ramping the water, but they are not moving at all. But then in that case, I would suppose there's just not enough pumping pressure through their mouth, and yeah, I don't think they're just getting enough oxygen supply that way.
They have to swim while they're sleeping too, right? The sharks, because otherwise they're going to just not have enough air, right?
I think so, but animals are like a little bit different from like human because some of them like they don't really sleep that much, and some of them they just fall half asleep. Yeah.
Where's your diffusion equation for the oxygen into the blood?
Yep. I think that's what we have here.
Basically, you just count how much water, and each of that water has so much oxygen. You can just only absorb. Basically, the faster you're the more oxygen.
Yep. Yep.
Okay, let's think. Calvin.
Thank you.
Mr. Hill's not here. I guess he's going to give it after you, or figure something out. Okay, so just come in the beginning of class and if you can set up on this computer.
You want to just log in?
Callan just logged in himself and then just set it up. That's probably easiest. It's fine. All right. That was the quiz day. 6. All right. So let's make a new page. The poor grader, he's going to fluids meeting next week, so he's not even start grading the quizzes. I'm guessing you'll get it after Thanksgiving, unfortunately. But his advisor said, "Don't push him, don't push him." So we'll get it back after Thanksgiving. I'm sorry it's so late this semester. Quiz 2 will be back after Thanksgiving. All right. Remember, there's no class Monday. I think by popular request, because I had to be out and do it online. So no class Monday. And the homework, I think we can make it due Friday. But since there's no class, if people need longer, you can ask me on Wednesday, or you can give a frantic group me on Thursday, and ask me if you need more time. We're gonna finish talking about complex potentials, and we're gonna talk a little bit about the homework. And then basically after Thanksgiving, we're just gonna do course projects. So there's a Google Doc. I'm gonna try to start going through these and make sure we have at least 3 presentations every day for after Thanksgiving. Okay. Yeah.
Because class periods are about an hour and 50 minutes long, should we not pace ourselves to 30 minutes if we are looking at like a lesser window to have our discussion? Because you want to fit three presentations a day, and each presentation on the subordinates list should be at least 30 minutes long.
30 minutes including Q&A and stuff like that. So like I think 20. I think you should have yeah, maybe make it down to like a 15 or 20 minutes presentation, and then some Q and have some Q&A and some demo. I mean, honestly, it's not super, unless it's like on your own research, it's not really easy to give like a very, very long talk. I'd rather have it be short and like people enjoy it than like, don't feel like you need to extend it just because you gotta like extend the time. But this is the course project for the semester to show. Let's talk about the course projects briefly. All right. Okay. So we that. Raise your hand. Let's have one person per group raise their hand. Let's see how many presentations we have. All right, one person per group, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 presentations. We got 11 presentations, and then 11 to, let's say 11 to 12 presentations, because there's some people not here. Okay, that's fine. A lot of people not here. 11 to 13 presentations. All right, and we got 3 class periods. So that is about about 4 per class period. And this class is 75 minutes, so you basically are going to have like around 15 to 20 minutes total per presentation. All right. So I mean, you've all seen these the journal clubs. Basically, some part's going to be like a journal club, but I would want to have some part that's like so leave some time for a demo, videos, and if you go into math, I thought the journal clubs did a pretty good job of not going into like a lot of algebra. Any math, I would say math, you can keep it to scaling or explain a final result. But we don't really have time to learn about physics and to go through the derivations. Because you imagine this is like like you go to a conference, 15 or 20 minute presentation, giving like a journal conference talk. For people to even understand what you're talking about, that takes a few minutes, and you got to have a few minutes to end, and then it's going to take time. So the math, you're going to have maybe a few equations that you talk about, but hopefully it's not going to be a totally theoretical thing. I do want to spend a lot of time on this, the demos and the videos, because I want this to be a fun last 3 days of class. As fun as possible. And the rubric, I talk about the grading, like basically originality. Like, did you actually, did you do something that like is not obvious what the answer is going to be, and did you come up with your own idea? Relevance to the class. I tried to push a little bit back on some things I thought were like basically like not super relevant to this class. Like there should be some fluid mechanics there. And engagement. Basically, you should be able to like fascinate your roommate or some random grad student about what you're doing. And if you can't, make it short. But it shouldn't, like you remember this course project, I give you total leeway to choose something. And you could choose something to torture yourself, or you could choose something that you're actually interested in. So choose something that set up the question, set up the clear question. Hopefully there's a clear takeaway. Set up a question and there's a takeaway. Okay, so people should be able to answer the question at the end, and hopefully use the video and the demos to sort of show that off. But we did a lot of stuff this semester, so hopefully you can show off some of that stuff. Does anyone have questions about their course project? Any questions about what they're going to do? Maybe just in we'll go around and give the title of your project, or just one sentence about your project. Okay. Daniel? One sentence. What are you going to present on? One sentence.
Capillary waves.
Next.
Training of single cells.
Stability of the vehicle.
Good. Next.
We are going to use the Schlerin camera to capture the flow properties of different surfaces.
Okay.
Microfluidic training of single cells with the stress response.
Okay. And you guys already
What
went.
he said.
Yeah. Go ahead. Guy time. Yeah. Or, yeah.
We are going to study the coffee ring effect and its industrial applications.
Taylor columns, doing a demonstration and then looking at it in nature.
I'll be talking about the influence of dimples on the trajectory of a golf ball.
I will talk about the fluid mechanics of dog lapping in the case of guinea worm disease.
It's a small-scale vortex generator to analyze motion of an inertial body in a rotational vortex. Stop.
CO2 plumes due to human breathing in a closed chamber.
Okay.
Just on teapot effect. Teapot effect.
Surface effects?
Teapot effect.
Oh, teapot effect. Okay. All right. So, yeah, I would urge you to have keep some of it in non-technical language. Basically, the best talks have. There's this guide for there's 1,000 most commonly used words in English. But basically, if you want people to understand you, you want to use as many of those words as possible. And then of course you have some in technical language. But you better be clear about you got to have some of both. For example, I think a lot of you did a good job summarizing your project in something that people can take away. Because keep in mind, we're going to be watching 13 presentations. It could be really, really boring if we're not careful. It could be really, really painful. And the audience will really appreciate you if you actually try to translate it. And there's always a danger when you try to translate it in words that non-technical stuff, you're going to be wrong. Of course there'll be regimes that they don't understand and that don't work, but at least they'll laugh and at least they'll get what you're saying. As opposed to being totally obscure. Okay, I'll write the word obscure. So we're going to have some combination of both of these. You could be totally precise and obscure, but they're not going to understand what you're saying because they're too tired. They're looking at their phones, and it's after Thanksgiving. So keep that in mind. We have very low brain power at this end part of the term. You want to basically, you don't want to assume you're talking to kindergartners, but you don't want to assume that people are going to be paying attention. You have to really grab their attention. So, and I think you saw this in the journal club. You saw what works and what doesn't work. Chances are, if you think it's too complicated, it's probably too complicated to talk about. You want to keep it pretty simple. And if you want, you can have the supplementary backup slides if we ask some really hard questions. But to be honest, 15, 20 minutes per presentation, we're not going to have. We're probably just time for 2 or 3 questions. And please audience, please stay engaged. It's your peers. If it's a really bad presentation, of course none of us are going to be paying attention. But if it's reasonable and people are putting effort, people put a lot of time into this, then I'm going to try to not look at my phone. And if you can do the same thing, that'll be good because I don't want to be the only question asker, because that's what's going to happen. So that's how we're going to end the term. I think it'll be fun. I think the people online, they're going to submit. Hey, anyone online? I don't think so. But if they're going to tell me what they do on GroupMe. I think we just take care of ourselves. All right. Any questions about the course practice? Everyone's ready to engage the audience. And for setup, I think just like we did for the journal club, there'll be 3 presentations 3 or 4 presentations per class. So I would say make sure it's downloaded, make sure it's ready to go before class. I don't want to spend 5 minutes you looking at Google to figure out your password and spending it'll just be a real energy killer. So make sure it's ready to go at the beginning. Assume you're going to present in the beginning of class because we're not going to wait for you. All right, that's the course projects. All right, so we had the nice quiz. We'll talk about that later, but we were basically talking about irrotational flow. All right, let's have a little review. There are 2 homework. So All right, we got 45 minutes today, which is good. We had 2 irrotational flow problems on the homework. One that's, and they're both a little different from class because these are 2D flows. In class was 3D flows, so the way we solved them was a little different. Okay, there's basically a potential and a stream function. They both give you information about the flow. If you calculate the gradient of the phi is the velocity field, and the curl of the psi is the velocity field. So they both contain information about the flow, and you can both use them to draw the flow. But we introduced this idea of complex potentials where we can do single calculations to figure out both phi and psi simultaneously. Okay. We have this notation that basically we have this variable z whose real part is the horizontal variable and the imaginary part is the y variable. This is good. We're not going for the quiz yet. You can record this. We're good. This is for the homework that you're going to turn in. Yeah, we're talking about the last homework. The last homework. Last homework. Before the final exam. Can you imagine if we had a final exam for this class? It would be so hard. It would be so hard. Even these quizzes, like if people are like falling like flies from the quizzes, the final would be like a. All right. So W has phi and psi. Okay, and basically, the derivative of W has information about the horizontal and vertical velocity. I'll call it the vertical velocity because we're in a plane, but it basically means the horizontal and the other velocity. Okay. All right. And we talked about a few examples of basically how to use this notation. For example, if W is given by this U naught would be, let's say U naught would be the basically the horizontal and vertical velocity, then W would look like this, and then dW dz is going to look like this, where basically that's the horizontal velocity and that's the vertical velocity. That's what we talked about a little last time. We talked about this last time, where basically the next, so the most simplest possible solution for this complex potential is a linear function, right? Just something that's proportional to z. You know, z is the complex variable, and this thing is a prefactor. So this is the kind of like the simplest possible solution. But it also gives you information on what the potential looks like, what the potential and streamlines look like. The next easiest possible solution for a complex potential is not just a linear, but a power, z to the power. Okay, and we said, hey, depending on what n is, you can have something that looks like flow in a wedge, which is really hard to calculate actually without this kind of formulation. And then we have n equals 1/2, which is flow around a plate. And we said you can play some tricks to figure out flows that wouldn't look like that. For example, if you have a flow that's called a stagnation point flow, that means you have an infinite plate, and in 2D potential flow, it just means you have an infinite line because there's no flow in the page. So infinite plate, basically, you're going to have something that looks like this, where in the middle of the plate you're going to have a stagnation point. I mean, of course, there's no real infinite plates, but if you have imagine you're like a mosquito stuck to the head of a car, like the beginning part of the car. Like when fluid hits a car, the fluid molecules see the car front as like infinite, like they can't see it. So basically in the middle of the car there's going to be a stagnation point where that bug goes bleh, and everywhere else it's going to go round. Okay, and to model this you just take this n equals 2 and you have this idea called the method of images, where you're going to assume the left flow is equal to the right flow. So we're not going to calculate both sides, we're just going to calculate the left side. Okay, and they call that stagnation point flow, and this is basically, anytime you zoom in into any kind of bluff body, it's going to kind of look like that. All right. Then we looked at the next possible function. Instead of a power, we looked at the log, which is kind of like the opposite of a power. Okay. And they said, hey, for sources and sinks, we have this looking at a log of z. And I think that's kind of where we ended it. Oh, we had one more. Okay. So sources and sinks are basically fluid coming in or out depending on the sign of M, coming in and out radially. And then if we basically the idea is if you switch the potential and the stream function, or you basically just consider you have the imaginary part here, then you have this irrotational vortex. And you're going to use this for the very last problem of the homework. Where basically there's no radio. So everyone likes to talk about irrotational vortex of everyday items, like toilet flushing. But the big difference between this and your toilet is that the toilet actually has some sink. Actually, some of the fluid goes away. Here, it's like you just, for some reason, you're a plumber and you stuck your hand in that toilet and you swirl it around. That's what you're going to get. And then hopefully you wash your hands before you eat lunch. But you don't have any sink. It's just like swirling around, okay? So that's why we have UR equals 0, and we have U theta goes inverse with R. So this is irrotational vortex, and this also satisfies that there's no vorticity for this. So del cross U is equal to 0. This is funny. It's called it's called irrotational vortex. That means irrotational, but there's still rotation. In this class, we won't have time to talk too much about. I think Ayo is going to talk a little about rotational fluid mechanics. But for example, this means that if you have like a little item here, I'm going to draw this little item. It kind of stays in the same facing the same direction as it flows. Objects don't like spin, because to get a vorticity, it means you actually have spin on a pointwise level. And here you don't have any spin, except for if you've got a little like a floating rubber ducky in the center. The floating rubber ducky in the center is actually going to be spinning around in circles, because the center it has a singularity, and you can't calculate the vorticity there. So everywhere else you don't have spin except for the center, where it's going to be spinning. And you probably saw that when you kind of flush the toilet. The thing in the middle is like going around. All right, then we have the doublet, okay, which is kind of, imagine you've got two dipoles a distance epsilon apart, okay? And basically flow goes from one to the other. All right, so let's continue on. Let's just go back. So that's what we did last time. So today, we talked about the method of superposition. This is what we mentioned briefly last time, that, remember, conservation of mass. So all these potential flows, so we're at high Reynolds number. So that means viscosity is small. High Reynolds number, viscosity is small. We don't solve Navier-Stokes equations anymore, because Navier-Stokes equations has viscosity. Instead, we just solve conservation of mass for potential flow. And basically, if U is equal to del phi, then del dot U, which is our conservation of mass equation, we've spent a long time with that in this course, that turns into del squared phi. This is called Laplacian phi. And we said, hey, that's why a lot of potential flows look a lot like heat transfer solutions, and that's why they look a lot like electromagnetism, because they all satisfy the same homogeneous equation. Well, basically, the idea of superposition, if you've got basically flow 1, U1 goes as U1 is equal to del phi 1, U2, where U2 is del phi 2. That means phi 1, if you basically, each of those satisfy Laplacian, then basically the sum of those are going to satisfy Laplacian. And you can create new flows out of adding irrotational flows. By summing irrotational flows. Okay. So all those basic flows we talked about, you can add them together and get kind of new flows. All right. And they don't call it summing because they want to sound sophisticated. They call it superposing. So superposition. For example, flow past flow past a half body. All right, this is what it looks like. Okay, so basically imagine you've got a uniform flow here, U naught. And then you have a source here, so uniform flow and a source. Imagine physically what's going on. A source means I'm sending fluid in all directions. Like physically, if I were to create this, I'd have like I'd have some water tunnel pushing fluid, and I'd have basically something that's spelling out fluid in 2 dimensions. So like I have like a kitchen faucet. Like imagine I've got my plate I'm washing in. I got the kitchen faucet coming down. That's sending out fluid like in all directions when it hits the plate. And if it hits the uniform flow, there's going to be a point that's called the stagnation point. So this is the stag point, right? That's where basically my kitchen faucet fluid velocity is meeting my uniform flow velocity, and the stag point is when those velocities are equal. So you basically, if I were to draw the streamlines, this half body means that. So the stagnation point is going to define what's called a stagnation point, a stagnation streamline. And in potential flow, steady state 2D potential flow, you don't have streamlines crossing. Therefore, streamlines can be used to imitate artificial bodies. So everything above that stagnation streamline is going to go above it. Everything inside is going to stay inside. Okay. So in this case, the complex potential W of z is equal to U naught z plus m over 2 pi log z. Okay. And so this is my uniform flow in the x direction, and that's my source. And what people do is you'll choose U naught and m as param to match your body of interest. And they use that, so they can use that to model, people use this to model internal or external flow. For example, external flow, if I redraw this thing, because that stagnation streamline, nothing crosses it, I might as well consider it to be a solid body. And then people can use this to model flow past this thing. Or people can use this to consider internal flow. Let's say you are at like a duck pond, or those ponds that have the paddle boat things, and they'll have like a little fountain here. Well, fluid can't go past the edge of the water, so you're going to get, if I have a fountain on the edge of the water, it's going to generate flow that looks like this. Okay. And these would be 2 separate problems you would study if you're trying to model the internal or external flow. Okay. Now, what's relevant for your homework? We got flow past a cylinder. We're going to add circulation in a second. Flow past a cylinder. So you have this thing. We talked about this dipole. You basically have the source and the sink really, really close together. So basically, flow is kind of going out and coming back on itself. Okay. So what that does is it creates kind of a cylinder shape. So this dotted line, remember in potential flow you have slip. It's not like you actually have no slip, but you have basically, the dipole itself just creates, so this is the uniform flow on this side. Flow past the cylinder. So this is U naught. So here you get the complex potential W of z is equal to U naught z plus, this is not great notation, m, but m is the strength of the dipole. Okay. All right. And for the homework, we're looking at flow past a cylinder with circulation. So imagine I have this same thing going on, but also I'm adding. Remember, I'm superposing. So I can draw my old stuff, but I'm adding this gamma. And we have this basically flow coming in with circulation. So we got everything we had before. Z plus. But now I'm adding this circulation. That's what you need for your homework. And remember, this is the irrotational vortex. Okay. So a rotating cylinder is the combination of the uniform flow plus the dipole to give you the boundaries, plus the fact if I want my boundary to have this spin, I add this. And remember, positive gamma is going to be counterclockwise. Positive gamma is counterclockwise, like shown. So basically, if I want to say I spin in the opposite direction, I give you negative gamma. But I think in the homework I would draw it's positive. Yeah. Z, they're all have both real and imaginary parts. So remember, Z is equal to x plus iy. So, I mean, a lot of you probably, if you've taken undergrad fluid mechanics, you've done this with just the potential, or you've done it with just the stream function. But by using this notation, z equals x plus iy, you can calculate the potential and stream function all together. And remember, the real part of, so the whole goal is to take dw dz, and the real part of that is going to give you your horizontal velocity, and the imaginary part is going to give you vertical velocity. Oh, is that Amber Alert? It's probably going to tell us there's another fire. These two fools, they had fireworks on near Cheshire Bridge, and basically it's like one of the worst fires in a long time. That's why there's actually smog here over the weekend, because it burned for 12 hours. For 12 fire trucks couldn't put it out. Any questions on complex potentials? We can also talk about it in the context of the homework as we start talking about the homework. Yeah.
To sort of, I guess, understand the system, the difference between this flow with circulation and the flow without it is just that there's now this gamma that's going counterclockwise.
That's right. So this is superposition. So if you look at these two complex potentials, here I just have the uniform flow coming from the left, and I have this dipole. And the way those interact is that basically this dotted line, I mean, if you do this problem, you'll find that there's two stagnation points. So this is stagnation points. Physically, you can imagine what's going on is like, the flow's coming out of the source and it's turning around and going to the sink, but it's hitting the incoming flow, so there's just two stagnation points here. And that's where u is equal to 0. And here is where the velocity u is equal to max, u max. Okay, because you got the source and the sink adding to the flow, so you have highest velocity there and lowest pressure. So you basically have the interaction between the incoming flow and the dipole creates these two stagnation points. Once you have three values, 1, 2, 3, it's much more complicated. Like the stagnation points will actually depend on what the relative magnitudes of gamma and m and u naught are. You could have situations that there's two stagnation points, one stagnation point on the thing and one stagnation point off the thing, and that'll also affect your lift. But just imagine you've got everything you have before, except I'm adding an additional flow. I'm adding this fact that this irrotational vortex, which says that the farther I get from here, the smaller my velocity, and that velocity is all in the azimuthal direction. So it's basically everything I got, plus I got this one more thing, and I'm figuring out the new flow field. It's like if I'm taking my cricket ball and I'm spinning it. So these potential flows are all used to model things that happen in real life. In real life, we actually have solid boundaries. We actually want to take things like this cylinder. It's like throwing a ball towards you or a cylinder towards you. We don't throw cylinders. We just throw balls. So throwing that towards you, if I don't spin it, I have flow past the cylinder. That would be the flow field, what it looks like. But if I do spin it, that's what I get. Into the page. So I'm spinning into the page. Yeah. These are all 2D flows. So if you're talking about a ball, it's kind of like what the flow would look like past the biggest outskirts of the ball. Yeah. And this is you're going to get, I think, you're going to get F lift, if I remember correctly, it's rho times U naught times gamma. As proportional to the density, proportional to the ball speed, and proportional to how much circulation you have. And remember, gamma is a way to tell you how much, kind of like how much spin I'm giving it. It's the integral of U around the boundary, but we use it to talk about spin. Okay. Physically, the reason why you get this lift force is that. And we talked about this a little bit before. So here you got some velocity. Imagine you got some velocity here. If I'm spinning it, you can imagine here, in this direction, I'm canceling out my velocity. So you could have U is equal to U small. And here, my spin is adding to the velocity. So this is U high. So if I've got a mismatch in velocity, my Bernoulli's theorem, which is perfectly valid in the irrotational regime, tells me that I'm going to have really high pressure on this side. U small, high P. And then I'm going to have a low pressure here, and this thing is going to go, it should go this way, F lift. So that's why they have the top spin, and they have the back spin. I don't know why they don't call it bottom spin, but that's why they do different things. They go in different directions. Like I think top spin goes down, I think. So that's that. Any other questions before we talk about the homework? We got 20 minutes. We got 20 minutes to talk about the homework. All right. And a lot of you have actually finished much of the homework, which is good. So you can focus on your course projects. All right. So the last homework. I wanted to give you one more. I feel okay about it. My homeworks are really long. Okay. The force per unit volume in a fluid. All right, let's go back. Let's go back a little bit. Remember Navier-Stokes equations equals to del dot T. All right. So remember. So Newton. They said, hey, we have this stress tensor, remember? Stress tensor. And this is a conservation of linear momentum where basically the units are force per unit volume. Force per volume, right? If you can't remember that, look at the left-hand side. This is like F equals ma. If I take rho times the acceleration, I multiply it by volume, I'm going to get a force. All right. And hey, we said we're going to write that as basically divergence of the stress tensor, where we said T, the stress vector, is going to have to be dependent on the direction. And we said, okay, well, there's going to be 9 components because you got the shear and you got the normal stress. So this is basically force per unit volume. Okay. And they said, we want to know the viscous force per unit volume. Okay. So this is del dot, we're going to substitute for the stress tensor, right? And this is basically, this is the viscous force per unit volume with a del. Okay. So you're going to have to basically viscous force per volume is equal to 2 mu del dot E. All right. So for number 1, you want to start with that, and this is number 1. And it says, hey, the viscous force per unit volume, we usually see that as something to deal with the velocity field. Remember, E was 1/2 del grad del U plus del U transpose, right? We know it in terms of the velocity field. That's what Newton said. That's why he got the name. They called it Newtonian fluids, because Newton said, hey, this rate of strain, T should have information about the rate of strain, and the easiest possible information you can have is the first derivative. And it turned out to be that. It turned out to be a really good approximation for most fluids. So the viscous force per unit volume is this, and you're supposed to show, in this problem, this is equal to nothing to do with U, but to do with the vorticity. Show this is proportional. So I'm going to put the word proportional because there's actually a negative sign in here. Del cross. It's going to be equal to the curl of the vorticity, where vorticity is the curl of the velocity. So it's going to be basically the viscous force per unit volume is related to the vorticity, and this is vorticity. This is getting to the part of the course that could be confusing because I just used W for complex potential, but hopefully you can figure out in terms of context. This W is not complex potential. This is vorticity. So what I would do for you, if I was you, I would sub in, use index notation to show that they're equal. So sub in for part A, and sub in for and use index notation for part B, and show that these two are equal. Okay. Index notation. It's really not very bad, not so bad. Does anyone have questions on? And I put this. So this proportionality means equal up to a constant. So there could be like a constant there, or a positive or negative, plus or minus. Okay. So it's, yeah. Okay, so thus demonstrate that that if it's irrotational, its dynamics may be prescribed by Euler's equations and the hydrodynamic force induced by integrating the fluid pressure. Okay. So what does that mean physically? Remember, it's irrotational. Irrotational, that means W, that means there's no curl. So if that's 0, then that means there's no viscous stress viscous force per volume. All right. That's what this shows, that there are two very different statements. One was about if a fluid is curl-free. This says that if I look at the velocity field and it doesn't have any curl, then I don't have any viscous force. I mean, it's weird. This is a statement just about the flow field, and this is a statement about physics, about like how much viscosity and how much dissipation. And it's saying if I got irrotational, I don't have this. And then thus conclude that basically is given by the Euler equations. So that means rho du dt, which is definitely equal to del dot t, is now going to just be equal to negative del p, right? Because the viscous force, 2 mu del dot E got killed because there's no if vorticity is 0, then this is 0. Okay, and these are called the Euler this is called the Euler equations. Okay, that's what they solve over in aeroastro. They don't have any viscosity, so they basically consider flows that are irrotational. So that's kind of like the big picture of the problem. This last part is just for your own information. Any questions about what you got to do for number 1? It's good? All right. Number 2, irrotational flow past the cylinder. All right, the key word here, if you want to get full credit, is past a cylinder. not past a sphere. What we did in class was a sphere, and there's the differences in terms of the way you do the vector calculus. Okay, let's draw a little diagram here. So cylinder here. So we're going to superpose a uniform flow and a uniformly translating cylinder. All right, so basically going to have a uniform flow going in this direction, U naught, and then we're going to have this going in this direction, U naught. Okay. All right. Okay, and so the sphere problem that we did before, we did the same thing, except the big difference is between spherical and cylindrical coordinates. So this is cylindrical coordinates, and this was spherical coordinates that we did in class. All right. A couple big differences. For example, cylindrical coordinates, basically you've got your u vectors. I'm gonna just use this. So you got your vectors. You got basically a. I'll call it a rho hat plus a phi hat plus a z hat. Okay. And for spherical coordinates, you basically have cylindrical coordinates. Basically, it's like a cylinder. You basically have that's your radius, and you have your angle phi, and then but you also have some position z. So this is like your position z. Spherical coordinates, you basically have your radius, and then you have got two angles. You have this angle, and you have the angle. This kind of from memory. I think it's like this. This is x and y. This is theta. But there are two angles. Okay, and one radial vector. So, for example, del dot A in cylindrical is going to look like this. Where you have basically a 1 over r term, 1 over your radius term here. And this is probably what's pretty familiar with. But spherical coordinates is starting to look a little more complicated. Okay, because you have basically a 1 over r sine theta here, because to get the units right, and del squared f. That's not del dot A. That's just that's del f. Sorry, del f. Gradient f. This is gradient f, gradient f. And del squared f, for cylindrical, you have 1 over r d rho of rho df d rho plus 1 over rho squared. Let's make a little column here. Right. And for cylindrical, this is what we did in class. We had this 1 over r squared d by dr of r squared df dr. And we basically ignored these other terms because we said it's like an infinite fluid and stuff shouldn't be varying in those directions. Oh, I gotta make this longer. All right, plus 1 over r squared sine theta d by d theta of sine theta df d theta plus 1 over r squared sine squared theta d squared f d phi squared. All right. So this is in gory detail. This is using the Wikipedia notation. All right. So let's circle what we did in class. Your class notes basically involves this, but for the homework, you should be using this. Okay, and notice that they have the same units, but the way you calculate Laplacian is different. So your answer is going to look a little, might look a little different. Okay. All right, so let's review how we did that in 3D. But first of all, any questions on cylindrical versus spherical and these two definitions of Laplacian? Because it's like because it's infinite. It's an infinite fluid, and axisymmetric. It's kind of honestly kind of hand wavy, but if you have more detail than that in your homework, I'll give you some more credit. But what we did in class, because in class we basically looked at 1 over r as solutions to this, so we ignored all these other derivatives. Yeah. Yeah.
Cylindrical, you have phi describing that angle away from the x.
Yeah, I think people use theta, but for some reason Wikipedia like to use phi.
Right.
I was going to change it, but I knew if I changed it, I'm just going to mess it up. So we're just going to use the terrible Wikipedia notation.
Dumb, but gonna ask anyway. I never did quite get how you got x's out of that when you are when you're differentiating with respect to r, not x. I understand dr dx
Oh, you mean
is x over r, but there d dr d.
It comes out of that node. Okay, it comes out of this identity that we showed. D x of 1 over r was like get it wrong by memory. But it has to do with the identity of how gradient. I think it's like this. It's like grad of 1 over r is x over r, something like that. Has to do with this grad. Oh yeah, this is like basically to do this you got to combine Cartesian and cylindrical. That's what it is. X is a position vector. This is a position vector. So r is always in 2D x squared plus y squared, and in 3D it's like basically plus z squared. And we said that in the homework. We said r squared was equal to xi squared, xi, which means the sum of all the components. Oh yeah, that's position vector. That's like equal to xi ei. Yeah. Yeah. It's just the position vector. Yeah. So the reason why you got to use Cartesian, because ultimately, like if you want to calculate horizontal force, like the velocity is in the horizontal direction. The velocity is in a Cartesian direction. So you kind of like got to go back and forth. You do go back and forth. But the cylinder, the geometry of the cylinder is described in cylindrical coordinates. So you have to go a little bit with both. All right, so number 2 on the homework, basically read, so number 2, why did it get so small? Oh, yeah. Oops. Yeah. In some ways, what phi minus 1 is just arbitrary. We just call it that. But you just got to make sure whatever you put in is still going to have information about v. It's still going to be linear with v, and it's going to be so you're still going to have to take a vector solution of v and dot it with. So to review, what we did with the in class before, we said basically. We said phi of x is going to have information about v and your position because you have your velocity of the fluid and you have your vector. So we did in class, we said phi, hey, the only way we can construct that is basically we're going to take a constant, their velocity, and we're going to dot it with what we called the second fundamental solution, phi minus 2. Where phi minus 2 was del of phi minus 1, which was del of 1 over r, which was x over r cubed. So this is what we did in class. This is for spherical. Yeah. Yeah, because you still have this basically, this still holds. You still need to have it, to have information on the velocity field and information about the fluid. But what this phi negative 1, negative 2, these are just kind of like arbitrary. We label them arbitrarily. We got to make sure they still satisfy what is now your new Laplace equation. And you got to apply your boundary conditions. And in some ways, it's an easier problem, but it's a little bit different from what we did. Yeah. So see if you can put in your boundary conditions. And I would redo what we did in class, and then see if you can do it with the new definitions of phi. Okay, 3 minutes here. Number 3. All right, so number 3 is the Magnus effect. Magnus effect. All right, Magnus effect. So here I gave you what the potential was. Okay. So I said, hey, phi is equal to theta gamma over 2 pi, and we need to use, but we need to you need to use the complex potential here. So you got to have omega of z, what we just talked about in class. So we got this constant times z plus m over z plus I gamma over 2 pi log z. All right, that's what we talked about today. And if you do this correctly, like you'll show that basically this associated with a cylinder A of radius A, where A is equal to square root of m over u. This is the radius of the cylinder. And of course, there's no real cylinder. There's no solid boundary. But the combination of those two flows, like what we had before, the combination of these flows, the doublet, creates like basically a stream. There's a single streamline that looks like this, that looks like A, that things can't cross. So we call that the cylinder. Okay. So what you're going to do is calculate dw dz, where you're going to calculate this by taking the derivative, u1 minus I u2, where u is going to equal to u1 comma u2, or u comma v. How do I use this notation? We call this u comma v, and we'll call this u minus iv. All right, so you're going to take the derivative of that. That's how you're going to get your velocity field. And you're going to make progress by setting z equals r e to the I theta, and then substituting in. This is the, I think this is called Euler notation. Okay. Yeah. So if I were to write this in more detail, this would be cosine theta plus I sine theta. Substitute that in, and then you're going to get You're going to get a nice solution for U. That's for part A of that problem. Part B, figure out the stagnation points. Part 3, integrate the drag. So remember the drag on the cylinder, F is equal to integral negative P n hat dA. So you're going to integrate this for at the cylinder where R equals to A. Calculate the horizontal and vertical velocity. And here you're going to have n hat is equal to cosine theta x hat plus sine theta y hat, if you want to separate the two terms. Because remember, when the cylinder's not spinning, you get was 0. That was D'Alembert's paradox. And it is spinning. I think I told you what the answer should look like, the lift force. All right. We're 3 minutes over. Let's just do the rest next time. I don't want to force people to be late to their class. So we're going to hear at least one course project next time. And I'll talk about the last 2 problems on the homework. I am physically going to go to DC for this APS fellowship meeting. So I will not be here starting Friday. But I will I'm going to have online office hours on Wednesday before Thanksgiving. I got to teach my other undergrad class, so I'm going to do office hours. So I'm going to probably do it during the daytime. Wednesday night starts to get into happy time. That's like holiday time. But I'll give you office hours. Three Musketeers are like kryptonite. This is like the candy everyone hates. Rolos, Three Musketeers, and my old earplugs. Sorry about that. Oh, I got 2 earplugs in here. Oops. And someone took some Starburst, but not all of them. They're like, yeah, I'll take some Starburst. Okay, so I'm going to do an office hours online on Wednesday, and I'll be here for a lot of the week if you have questions on the homework. I'll be in my office from 12 to 3:30 today. Yeah, what's up?